At the same time the Curies were in France, another scientist named Ernest Rutherford was in England at the Cavendish Laboratory, busy doing his research on those same rays. Before he was in England, Rutherford was simply a student working on a potato farm in his native New Zealand. Rutherford had applied for a scholarship to Cambridge University, one of England's most famous universities, and actually he lost the scholarship, finishing second. Only the first place got the money. But the winner decided to stay in New Zealand and get married. When Rutherford found out that he had actually won the scholarship, he put down his potato fork and declared, "That is the last potato I'll ever dig." And he went on to become one of the greatest scientists of the 20th century. At Cambridge, he worked for J.J. Thomson in the Cavendish Laboratory, busy doing his research on those same rays that the Curies were interested in. Virtually all of those scientists knew each other, and many, like Thomson and Rutherford, became good friends. In fact, here's a picture of Thomson and Rutherford as young men, and here, later in life, still good friends. So, uranium gives off rays that can be detected by a sensitive electric meter. But just how strong were those rays? Rutherford decided to put several sheets of foil in between the meter and the uranium to find out how strong the sample really was. As each sheet was added, the meter dropped off rapidly. Then, to his surprise, it leveled off but continued to still register some kind of radioactive particle. Something was getting through the foil. So, Rutherford discovered there were actually two kinds of rays or particles coming from the uranium. This was getting complex. One was a weak particle that was initially stopped by one foil layer. The other was a more penetrating particle that went through several layers of foil. Two kinds of radioactive rays or particles. And since he discovered them, he got to name them. So he named them A rays and B rays. But to his credit, he decided to use the Greek words for A and B, and he called the heavy ones alpha rays, and he called the light ones beta rays. Rutherford continued his work on these rays and other physics projects, eventually becoming the head of the physics department at the University of Manchester, England. Rutherford was wanting to do an experiment that required lots of A and B particles, but the uranium he was using just couldn't crank them out fast enough. It was like trying to burn this entire brush pile using this little dinky lighter. There just wasn't enough fire, enough alpha and beta particles to get the job done. Apparently, it was really quite frustrating. What he needed was something way stronger than uranium in order to crank out enough alpha and beta particles. But where was he going to get that? As destiny would have it, one summer a little celebration in Paris was given for Marie Curie for her recent discovery of radium. And Rutherford, who was getting pretty famous himself at this point, was invited to the party. Of course, he jumped at the chance to travel to Paris and meet Marie and Pierre. One evening, after talking over his dilemma, Marie and Pierre actually gave Rutherford a strong radioactive preparation of their rare and precious radium. Pierre declared radium to be nearly 1,000,000 times stronger than the uranium Rutherford had been using. Now he had something that could really crank out alpha and beta particles. It was like exchanging this uranium lighter for a radium flamethrower. Rutherford was delighted. Back home, he placed the radium in a lead box. Then he poked a hole in the end. With millions of alpha and beta rays blasting around the inside of the box, A torrent of invisible but powerful rays was streaming out of that hole. In effect, Rutherford had made an atomic ray gun, which made Rutherford the first true particle physicist because he used beams of particles as projectiles to explore the structure of matter. And what did he do with his ray gun? Well, it seems like the first thing any scientist does with something like this is they expose it to a magnet, because the ability to affect something with a magnetic field is the infallible signal that whatever's being affected is electrically charged, very much like our magnets here. Opposite sides attract, like sides repel. The alpha rays seemed quite a bit heavier and bent a very small amount in one direction. But the beta rays were lighter or smaller and really bent toward the positive end of the magnet. That suggested that the beta rays were negatively charged because opposites attract. Something bending toward the positive end of a magnet suggests that whatever else it is, it's negatively charged. Plus, because it curved so easily, it must be lighter than the heavy alpha particle, which didn't curve as much and probably had a positive charge. Rutherford's old boss, J.J. Thomson, had just discovered the electron a mere 365 days before Rutherford's experiment. Thomson showed that electrons were negative particles that bent toward the positive side of a magnet. In fact, if you think about it, Thomson's experiment and Rutherford's experiment were exactly the same, except Thomson got to use a cathode ray tube, and Rutherford was to use the newly discovered radium. Both got exactly the same results: particles that weigh the same, that are negatively charged and pulled toward the positive side of a magnet. A little more research confirmed that Crookes' cathode rays, Thomson's electrons, and Rutherford's beta particles were all the exact same thing. Different names that different scientists used in different experiments, but we're all seeing the exact same thing: electrons. That's why they all curve easily toward the positive end of a magnet, because electrons are lightweight and negatively charged atomic particles. You can't have a solid plum pudding model if you've got particles flying out of your pudding all the time, and it appeared as though the plum pudding model was disintegrating in front of their very eyes. So the atomic theory went from a solid billiard ball to a plum pudding to what? Well, it was Rutherford's next experiment that would forever end the plum pudding model of J.J. Thomson. Thomson's star student, Ernest Rutherford, was about to demonstrate that the atom was even more complex than Thomson could ever even imagine. By the way, what kind of a man was Rutherford? Well, according to his co-workers, he was a big and rather clumsy fellow, with large blue staring eyes and a damp, pendulous lower lip. As he talked to his companions in the street, his voice was easily 3 times as loud as any of theirs, with his New Zealand accent. He was fun, outgoing, and vigorous, the life of the party, a great big, overgrown adolescent. This is Ernest Rutherford, preeminent scientist of the 20th century that we're talking about. He loved science, New Zealand, his wife Mary, and he loved to golf. He and Marie Curie became good friends. He was also a hard-working scientist who loved science for itself and never tired of playing in the laboratory. He was bigger than life, Ernest Rutherford, and he liked the success, the flattery, and the titles of the high-minded society. Upon meeting people like Einstein and Lorentz and Planck the very first time, he was able to turn them into immediate best buddies. Most people apparently really liked Ernest Rutherford. Several years after discovering alpha and beta particles, Rutherford moved to England and became the head of the physics department at the University of Manchester. At one point in 1909, Rutherford set up an experiment to test if Thomson's model of the atom was accurate. Using his ray gun in a box, the heavy alpha particles would blast out the end like a machine gun. Now, beta particles, electrons, are also shooting out, but they are so incredibly small and unbelievably light that their influence would be insignificant in the experiment. So, he's got his ray gun, but what should he shoot his heavy alpha particles at? See, here's the problem. Rutherford, and nearly everyone else, was working hard to try to understand how atoms were designed, how they work. If an atom really were the size of this muffin, you could experiment on it directly. You could cut it, or you could X-ray it, or weigh it, or put chemicals on it. But atoms aren't the size of this muffin, not even close. So Rutherford thought if he took his ray gun and could hit an atom directly, maybe it would tell him something about the inner workings of an atom. What he really wanted was to design a wall of atoms that was as close to 1 atom thick as possible. Good luck. But incredibly, Rutherford did get close. And for his target, Rutherford chose a really thin sheet of gold foil. Are we talking about thin like this foil thin? No, we're talking about something like soap bubble thin. Well, before we talk about the how, let's talk about the why. Why gold? Gold is known to be fairly unreactive, is fairly dense, and is the most malleable metal known. That means gold can be hammered into a very, very, very thin foil because its atoms are so tightly packed together. In fact, gold can be hammered into a foil so thin that light will pass through it. Gold is dense, and a cube 3 inches on edge can be pounded into a sheet that covers this football field. That's malleable. That's just what Rutherford needed. He wanted his foil to be about as close to 1 atom thick as possible, which is highly unlikely since human hair is about 1 million atoms thick, and this foil is about as thick as a human hair. But as incredible as it sounds, Rutherford was actually able to make his foil about 400 atoms thick. And you might be asking yourself, how in the world could a guy that lived 100 years ago be able to make foil that is 2,000 times thinner than a human hair? Well, by using a vacuum chamber so there's no air inside. Then, evaporating a little bit of gold in the chamber, a thin, dust-like layer could be deposited on an ultra-pure, ultra-thin glass slide. Actually, it wasn't Rutherford himself who carried out this experiment. Rutherford was known for promoting his students' work and for giving credit to others whenever possible. Although he designed much of this experiment, he had his assistants, Hans Geiger, and a 19-year-old undergrad named Ernst Marsden do the work as a research project. Now to the how. The famous gold foil experiment was carried out in Rutherford's laboratory in Manchester and looked something like this. Now remember, what Rutherford wanted to do was experiment on atoms by shooting alpha particles at them, maybe to see how an atom was constructed. So the first thing he built was a ray gun, a lead box with a small amount of radium inside and a little hole so the particles will shoot out. The ray gun is mounted here. Now, obviously, particles from the ray gun are way too small to see, so they needed a way to see them, or at least detect them. Enter this green screen. Remember how Röntgen saw the board glowing a few feet away from his cathode ray tube? And remember how Marie Curie's little vials of radium glowed beside her bedside? By this time, it was well known that radiation itself doesn't glow. Other stuff glows when the X-rays or electrons hit it. The reality is that radioactive material looks just like this chunk of metal, or liquid. In fact, this is a chunk of weapons-grade plutonium. No glow. The end of this was coated with a mixture of zinc and sulfur, which is the most common phosphorescent material used for glow-in-the-dark toys. Geiger and Marsden took a bit of screen material and coated it with this zinc sulfide. This is how they are going to see those little particles. Because now, when a particle shoots out of the ray gun and hits the screen, it will give off a microscopic spark of light. Notice I said microscopic spark. In order to see something microscopic, you need a microscope. So they took this small but powerful microscope and mounted it on this turret device. Then, they took the small green screen and mounted it on the front of the microscope. Now, when a particle hits the screen and makes a little flash, they can look through the microscope and see the microscopic flash. Now, what about the thin gold foil? Well, it goes right over here. When particles shoot out of the radium ray gun, they will shoot directly at the gold foil. The microscope and screen swivel and can be set at any angle around the gold foil. Now, if J.J. Thomson's model of the plum pudding atom is correct, the particles will slightly deflect off by a degree or two and hit the zinc sulfide at the other end, making a little flash on the screen. This tube in the middle pumped out all of the air so the atoms in the air wouldn't interfere with the experiment. Finally, they topped the device with glass. The experiment itself took a great deal of patience and was quite tedious. It was necessary to spend the first half hour or so in complete darkness. That way your eyes would adjust and become sensitive to the tiny flashes of light. Geiger and Marsden would sit in the dark, drinking tea, gossiping, and trading jokes. Eventually they got back to work, and one of them would adjust the microscope to a particular angle, then look inside and begin counting all the flashes they saw on the zinc sulfide glow screen. Each observer could accurately count about 90 flashes per minute for only a few minutes before they needed to trade places. Marsden and Geiger would ultimately count hundreds of thousands of the tiny, short-lived flashes, or scintillations, as they called them. It was difficult and tiring work. Rutherford, on his daily roaming through the labs, would often stop by and join them, but he lacked the patience and the younger eyes needed for scintillation counting. Geiger, on the other hand, was incredibly persistent in his counting work. In fact, he later invented a device, very much like Pierre Curie's machine, that would electrically and automatically count all of the particles, even in broad daylight. It became known as Geiger's counter, and the Geiger counter is still used today to detect and count radioactive particles. What did they discover from their gold foil experiment? Well, most of the particles did not deflect off slightly as they thought. Most of the particles simply passed straight through the gold foil. But even more strangely, many of them consistently scattered off at very sharp angles. And the strangest of all, when they moved the screen right next to the ray gun, they found that about 1 in 8,000 alpha particles actually came ricocheting straight back at the gun. What was that all about? After puzzling over these results for nearly 2 years, Rutherford concluded that the reason the alpha particles passed straight through the gold foil wall was because atoms were mostly made up of empty space. And the reason some of them ricocheted backwards was because at the middle of each atom was a positively charged center, a kernel, made up of densely packed positive particles, just like the alpha particles they were shooting were positively charged. And two positives repel each other, just like two magnets. And when they came directly at each other, the alpha would bounce directly back at the particle ray gun. Rutherford said it was like shooting a 15-inch shell at a piece of tissue paper and having it ricochet back at you. It was reported that Rutherford got so excited over these discoveries, he would roar in triumph and begin singing "Onward, Christian Soldiers," because it was virtually the only piece of music that Rutherford actually knew. He also sang it out of key. Then he would begin doing the New Zealand haka war dance, yelling and stomping around the lab in triumph. Kamate, kawa, kawa, or something like that. Apparently, Rutherford was a lot of fun to be around. From their research, they determined that the nucleus was only about 1/100,000th the size of the entire atom. If you scaled the nucleus up to the size of a quarter, the entire atom is over 1.5 miles across. Rutherford called the center of the atom the nucleus, which is the Latin word for nut or kernel, because the nucleus acted like a hard nut, like this macadamia nut, the hardest nut in the world. This led Rutherford to propose that the atom was nuclear, that it had a nucleus in the center, and it was this experiment that launched science into the nuclear age. For his discoveries, Rutherford was awarded the 1908 Nobel Prize in Chemistry. He actually somewhat resented that the prize was in chemistry rather than physics, and his acceptance speech made a remark to the effect that he had seen many transformations in his studies, but the quickest he had met was his own transformation from a physicist to a chemist. Rutherford thought that all science was either physics or nothing else. In a famous quote, he said, "All science is either physics or stamp collecting." It must have been a trifle embarrassing to receive the Nobel Prize for stamp collecting. Based on the gold foil experiment, Rutherford proposed a whole new model of the atom, the planetary model. As the planets are held in motion by gravity, so electrons are held in motion by electrical and magnetic forces. Rutherford proposed that the atom contained a massively heavy nucleus made of positive particles he called protons, containing all of the atom's positive charge. Flying around this positive nucleus were an equal number of very lightweight and negatively charged electrons. Even though they are far away from the nucleus, they are equal in number, so the atom is electrically neutral. No shocks when you touch it. That's what electrically neutral means. Most of the alpha particles shot from his ray gun didn't scatter much because they were passing right through the empty space of what appeared to be a solid atom. Unlike his friend Marie Curie, Rutherford never showed any signs of radiation sickness throughout his lifetime. If you hunt around a bit with a Geiger counter on Rutherford's desk in Manchester, you can still find traces of radioactivity more than 100 years later. It actually cost over $100,000 to decontaminate the famed physicist's desk before it was deemed safe for display in Manchester. Rutherford wrote several books on radioactivity and on the atom. He was knighted in 1914 and served as president of the Royal Society for several years. He was honored with an amazing array of medals and prizes and awards, possibly the greatest assemblage of scientific medals in the world. And along with his degree from the University of New Zealand, he was awarded honorary doctorates from 20 other universities. Scores of houses, buildings, streets, and institutions bear his name. Element 104, Rutherfordium, is named after him. A small crater on the edge of the Mendeleev crater, plus a crater on Mars, both bear his name. We remember Rutherford for his discoveries, but also for his humility in giving his coworkers more than due credit. Often he would do the preliminary research, then hand the topic off to a colleague or a student, and they would get all the credit. He didn't even put his name on a third of the groundbreaking research papers and discoveries, even though he initiated almost every investigation. Rutherford is considered the greatest experimental scientist since Michael Faraday. His image is on the New Zealand $100 bill. Ernest Rutherford, the father of nuclear physics, died in Cambridge on October 19, 1937. His ashes were buried in the great Gothic church of Westminster Abbey in London, England, next to the tombs of Sir Isaac Newton and next to his friend, J.J. Thomson.